Hello, good evening, everyone. So today is the last session, live session for this course, NMR Spectroscopy for Chemists and Biologists. So it is a 1 hour course. So, I will wait for 2 minutes and then I'll start the course. So today what we will do, we will just revise the main concepts that will help you through your this course exam, the exam of this course. And we will revise all the concepts, and one more concept we will look in a bit more detail is STD NMR, or saturation transfer difference NMR. So if you have any doubts, you can ask me, because after this we will not be having any more session. Okay, so let's start today's session. So I'll share the slides. Yeah. I hope the slides are visible. Yeah, so hello everyone, I'm Akash Jyoti Pathak. I'm a PMRF TA for this NPTEL course, NMR Spectroscopy for Chemists and Biologists. This course is being taken by Professor Ashutosh Kumar and Professor Hosur. And so today is the last session for this course. And yeah, so I'm Akash Jyoti Pathak. I'm a PM. So I am a PhD student in the Department of Biosciences and Bioengineering in IIT Bombay. So let's start with today's session. Uh, so yeah, so we will revise quickly whatever concepts has been taught throughout this entire course. Starting from in the first week, we saw the basic concepts of NMR spectroscopy. What is basically an NMR spectroscopy? So herein you have uh, the main component of an NMR spectroscopy is what it is. It is a nuclei, right? As the suggests, nuclear magnetic resonance means here it is the nuclei. And as we know, that nucleus has a proton and a neutron. The neutron is chargeless and the proton carries a +1 charge. And because of this positive charge, it is spinning, it produces a magnetic moment of its own. And so in absence of the magnetic field, right? In absence of the magnetic field, when our sample is present, so the sample is made up of atoms, right? And so the sample will have new as an atom consists of nuclei, so the sample will have nuclei. When this sample is placed in a magnetic field, what happens is there is there is the degeneracy of energy is lost, and we get two energy levels, the alpha state and the beta state. right? The alpha state is the lower energy state and the beta state is the higher energy state. So in absence of the magnetic field, the nuclei are randomly oriented. But when this sample is placed in the magnetic field inside an NMR spectrometer, the nuclei distributes between these two energy levels, right? So as alpha state is the lower energy state, more number of nuclei usually remains in the alpha state, and the lesser number of nuclei are present in the beta state. And what happens is the energy difference between between these two states is what it is. It is gamma Delhi. The energy difference is equal to gamma H B naught, right? Right. When we apply a radio frequency, having the energy equivalent to the energy difference between these two energy levels, the nuclei will transition from the lower energy state to the higher energy state. And so each nuclei will have its own characteristic frequency, right? Will have its own frequency, and when an energy uh, equivalent to the frequency of that nuclei is applied, right? The nuclei will undergo transition. And so once it undergoes transition, this is what gives the signal in an NMR spectrometer, these transitions. So, so as we learned that, so let's start with the first point. So what does the first point say? It says that the strength of the magnetic field. Yeah, the strength of the magnetic field in an NMR spectrometer is given in terms of the Larmor frequency of the proton nucleus. So what is the Larmor frequency of the proton of a nuclei? So we learned that there is an external magnetic field, right? There is an external magnetic field, and when this nuclei is placed in the external magnetic field, the nuclei experiences a torque. And since the nuclei experiences a torque, it starts precessing, or it starts rotating around the external magnetic field. So the frequency with which it rotates around the external magnetic field is called the Larmor frequency. Is called the Larmor frequency of the nucleus. So each nuclei, a different nuclei, NMR active nuclei will have their characteristic Larmor frequency, depending on what? Depending on the gyromagnetic ratio. Okay, so depending on their gyromagnetic ratio, each nuclei will have its own Larmor frequency, and so Larmor frequency is given by this formula: omega naught equal to gamma b naught, omega naught equal to gamma b naught, if you in terms of frequency, what will it be? So we know that omega equal to 2 pi nu, right? 2 pi nu. So if you express this omega naught in terms of frequency, then you will get gamma b naught by 2 pi, right? Gamma b naught by 2 pi. And so this is the frequency with which it is rotating around the external magnetic field. Now the proton, each nuclei has its own gyromagnetic ratio, as I was mentioning. So the most commonly used nuclei that is used in an NMR spectroscopy is the proton and the carbon-13 nuclei. N15 is also used, but most of the questions are usually asked on proton and carbon-13. So it is better if you remember the gyromagnetic ratio of proton and carbon-13 nuclei. So the proton has a gyromagnetic ratio equal to 26.753 radian per Tesla per second. Okay, or in terms of megahertz per Tesla, this is how much? This is 42.57 megahertz per Tesla. Okay. And C13, carbon-13 nuclei, it is a comparatively less sensitive nuclei because its abundance is 1.1%. So here, so the sensitivity of an NMR active nuclei depends on what? So it depends on the abundance, it depends on the gyromagnetic ratio. There are other factors also. We will learn them as we go through this session. The carbon-13 has a natural abundance of 1.1%, while hydrogen, proton, has a natural abundance of 99.98%. Okay, so try to remember the value of the gyromagnetic ratio of proton and carbon-13, and also the natural abundance of at least these two nuclei. One is carbon-13 and another is proton. Now, Now, what will be the spin quantum number of different NMR active nuclei? So, an empirical rule is followed over here. So, we discussed all these in week one. If you remember them, you know this point that nuclei with the odd number of atomic numbers and even atomic mass numbers. Okay, so for example, this N14. So N14 has an atomic number 7, right? And mass number is 14. Okay. So similarly, this is what? This is deuterium. H2, or it is also known as deuterium. Deuterium has a mass number of 2, atomic mass number 2, and the atomic number is 1. Boron. Boron has an atomic mass number 10, and its atomic number is 5. Okay. If the nuclei, so for nuclei which are having even atomic number, even mass number, even atomic mass number, and odd atomic number, they have integral spin values. Integral spin values means what? Integral spin values means they will have I equal to 1, 2, 3, 4 in this, and so on, right? So that is the spin quantum number, or I, the value of I for nuclei with odd atomic number and, yeah, even atomic mass number. Similarly, nuclei with even atomic number and even atomic mass number. So if both the atomic mass number and the atomic number both are even, then in that case we say that the nuclei is NMR inactive. Why is the NMR inactive? Because in that case both the neutrons and protons are paired with each other, and so we will not get any signal for these nuclei if they are, if NMR spectra is recorded for these, or if they are, if such sample is put in an NMR spectrometer. So they have I equal to 0, right? I equal to 0. So if the spin quantum number is 0, then the magnetic moment will also be 0. Nuclear magnetic moment will also be 0, because what we know, mu equal to gamma into I, right? So if the spin quantum number is 0, then the nuclear magnetic moment will also be 0. While so these are the two cases. While for other cases, if there are uh, if the atomic number, mass number both are odd, then we will have half integral multiples, or and so on, right? So this is what I was explaining. So in the presence of an external magnetic field, so when the nuclei is placed in an external magnetic field, the nuclear spins can exist in two states. It can exist in the alpha state or the beta state, right? The spins in the alpha state point in the positive z direction, while spins in the beta state points in the negative z direction. So you remember I hope you remember this figure, that whenever this is placed in this external magnetic field, the qua- the classical mechanical picture of how this nuclei gets, or the how the nuclear spins gets arranged in the alpha and the beta state, and because the experience is stored, they start precessing in the form of a cone, around the external magnetic field. So the alpha state, the alpha states, near the nuclei which are in the alpha state, they point in the positive z direction. So if you take a vector addition of the nuclear spins which are in the alpha state, you will see that the net magnetic moment exists in the positive z direction, and the nuclei which exist in the beta state, they are rotating around the external magnetic field in a along the negative z direction of the magnetic field. Okay. Okay. Now, then um, what is the main uh, the NMR signal that we get? What does it depend on? So, what will be the main thing that controls the NMR signal that we will be getting? So, it is the population difference. So, it is the population difference between the alpha state and the beta state that determines the NMR signal, right? So the population difference between the two nuclei is given by what? It is given by the Boltzmann's law. So I hope you remember this formula. So gamma H B naught. This is delta E. Delta E. This is the energy difference between the alpha state and the beta state divided by the Boltzmann constant into the absolute temperature. So the difference, the ratio of so n beta is what? The number of nuclei in the beta state, and n alpha is the number of nuclei in the alpha state. So the ratio of the number of nuclei in the beta state and the alpha state is given by this equation, which is known as the Boltzmann's equation. So it is e to the power minus gamma h b naught by kt. So if you look at this equation, then how will you? So the more the difference between the two energy levels, or between the two states, between the alpha state and the beta state, the better will be the NMR signal. Okay, so that is why you see this energy this ratio is directly proportional to gamma. It is proportional to the magnetic field. So if we increase the magnetic field, if we use a nuclei which is having a higher gyromagnetic ratio, and if we lower the temperature, then we will see that the difference that this n beta by n alpha, this ratio increases, and hence we get a in the in for these nuclei, they will have a higher difference between the two, or higher difference of nuclei between the alpha and the beta state. Now, relaxation. One more concept that we learned is relaxation. Relaxation is a phenomena where the magnetization returns back to its equilibrium position, which is the positive z-axis. So, in what we do in NMR in an NMR experiment, what we do, we first put the probe inside the NMR spectrometer, and then some time is allowed for equilibration between the two state, which is known as the this is also known as the delay period for so that the system can attain equilibrium, and then short RF pulses are applied. Why are they called RF pulses? Because these RF radiations, they are applied for a very short duration, that is in the microsecond time scale. That is why they are called RF pulses. And once this RF pulses is given to the nuclei or to the sample, what will happen? These nuclei will shift um, they will be shifting from the positive, or they will shift from the XZ plane to the XY plane, right? XY plane, or the net magnetization. The net magnetization flips, or it shifts from the positive Z direction to the positive X axis. Depending, or it can shift to the positive X axis, or it can shift to the Y axis, depending on in which direction we are applying the RF pulse. Okay, so once this RF pulse is removed, then what will happen? Once the RF, the nuclei, they will start relaxing. They will start moving to their equilibrium position. So the time, so that is the T1 relaxation. T1 relaxation is also known as the longitudinal relaxation. It is also known as the longitudinal relaxation or the spin lattice relaxation. So what will happen? This magnetization vector, it will start shrinking in the x direction, and it will start elongating in the z direction. So that time that is required, that is T1 relaxation. And what is T2 relaxation? T2 relaxation is called spin relaxation or transverse relaxation. So once this RF pulse is applied, there is coherence, or all the spins that were nuclear spins that were randomly oriented uh, around the they were randomly oriented around this cone, right? They were randomly oriented. Once this RF pulses is given to them, they attain coherence, or they merge together and they become oriented along the x direction. For example, if the pulse is given in the negative y direction, then this magnetization will orient itself in the positive x direction. So this is called phase coherence. Phase coherence, or that is called phase coherence. And once this RF pulse is removed, they will lose this coherence, and they will start dephasing out. They will start dephasing out, and they will move to the positive Z direction. Right. So that time, that is called the T2 relaxation. So what happens during the T1 relaxation? The magnetization, the bulk magnetization or the net magnetization, that goes from the x-axis to the z-axis. And during the T2 relaxation, the things transition from a coherent state. Why? Because the view, I hope you remember the random approximation. Random phase approximation states that all the spins are randomly oriented, and they are randomly oriented around this cone, and they're precessing around this external magnetic field. So once this RF pulses are applied, they move to a coherent state in the positive x direction. And when the RF pulse is removed, they move from this coherent state to the decoherent state. So combining the two relaxation, the spin moves to the z-axis by spiraling out from the x-axis. So if we consider both this T1 relaxation and T2 relaxation, then the spin will follow a spiral path. And following a spiral path, it will move to the spins will follow a spiral path, and the magnetization will shift to the z axis. Okay. This is clear. Now, okay, so let's discuss these questions. I have not added the this slideshow I have not done for this questions. So the first question is the FID of a sample was observed to have. Just give me a second. I will just connect the. Mm, Okay, let's discuss this because this is only a 1 hour session. So let's discuss this uh, orally. So what happens is, so in this question, the FID of a sample was observed to have decayed by about 40% at 100 millisecond. Based on this, which of the following would most likely be the T2 relaxation value of the sample? Now, you see this figure, okay? The T2 relaxation, this T2 relaxation, so there is a decay of the signal, right? So once this RF pulse is removed, the there will be the spins will start relaxing and they will move to the z-axis. This decay in signal, this is given by e to the power minus t by t2, and the FID that we get, the FID is a combination of this oscillation and this decay, e to the power minus t by t2. So it is combination of cos omega t into e to the power minus t by t2. Now what in this question here is I have asked is that at 100 millisecond. So in FID, you are recording the signal, and this time is plotted and this in the x-axis, along the x-axis, and you are recording the signal. And you see here that S is S. So this signal that you decay signal that you will get, that is given by this formula, S equal to S naught e to the power minus t by t2. And so at 100 millisecond, yeah, it is saying that the signal has decayed by 40%. So how much signal is remaining? 60%, right? 60% signal is remaining. So 60% signal means we can write it S equal to 0.6 S naught. Now, if you calculate this, if you substitute the value of S equal to 0.6 S naught in this equation, and you put the value of T equal to 100 millisecond, then if you solve this by taking ln on both sides and you solve the value of T2, you will get the value as 195.761. And so this is approximately equal to 200 millisecond. Okay. So here in this question, you are recording the FID of a sample. So remember this FID signal, it is combination of this oscillation and the decay signal. Okay. So this is the expression of FID. So it is cos omega t e to the power minus t by t2. And so so this cos omega t is actually the this is the signal. This is the 60% or this is S naught over here, right? This is S naught over here, and then you substitute this value, you will get this answer. Okay. So such type of questions. So this is one of the example, right? And then moving to the next question, which of the following will decrease the difference in population between the two energy levels, alpha and beta, in a spin half system? So there are four options: increasing the temperature, increasing the external magnetic field, increasing the sample concentration, and increasing the gyromagnetic ratio. So what will be the answer? So it is asked which will decrease the difference in population between the two energy levels. So if you want to decrease the difference in population, so increasing the gyromagnetic ratio will not help. Increasing the sample concentration will also not help. Increasing the external magnetic field will also not help. So the answer for this question is increasing the temperature. Okay. Now, moving to the next question, under which of the conditions the population will be 100% in lower alpha state? So I hope this I understood this question. So just now we were discussing the what will be the population difference between the two levels, alpha state and the beta state. So you remember this Boltzmann law, n beta by n alpha equal to e to the power minus del E by kt. So you see that this population ratio, this ratio is directly proportional to the gyromagnetic ratio. It is directly proportional to the or exponential. It is in the exponential order. Those on increasing the external magnetic field, increasing the gyromagnetic ratio, increasing the sample concentration, they will yeah, increase the difference in population. But here in this question, you have been asked to find the decrease, which factor will decrease the difference in population. So if we increase the temperature, then there will be difference in population, decrease in difference in population. Okay, we need to lower the temperature for increasing the difference in population. Now answer this question: under which of the which of the conditions the population will be 100% in lower state, lower alpha state? So if so for this question, the answer is at 0 Kelvin. So at 0 Kelvin, what happens? At 0 Kelvin, all the spins at 0 Kelvin, all the spins are in the lower energy state or the lower state, the alpha state, right? So and what happens at high temperature, at infinitely high temperature? At infinitely high temperature, it will lead to a saturation condition. What is a saturation condition? A saturation condition is a state where the number of nuclei in both the alpha state and the beta state are equal, right? So the 100% population will be in the alpha state. So these are the two extremes of temperature at 0 Kelvin or at right at 0 Kelvin. This is the lowest temperature. At lowest temperature, all the nuclei will be in the alpha state, and at higher temperature, what will happen? There will be saturation of the spin population. Now answer this question: after the application of 90-degree RF pulse, the spin pointing. So the answer for this question is at 0 Kelvin. And the answer for this question is option A, increasing the temperature. After application of 90 degrees RF pulse, the spins pointing in which direction? So when you apply a 90-degree RF pulse and considering that the bulk magnetization is oriented in the positive Z direction, right? The spins will be pointing in the spins will point in the XY plane, right? So the this magnetization, this bulk magnetization or the net magnetization is in the oriented in the Z direction in the equilibrium condition. Now once RF pulse is applied, this flips from the Z direction and moves to the XY plane. Okay, it moves to the XY plane. Okay, so now we will look into the next concept. So now coming to next in the session, in this lecture, we had looked into chemical shift. We had understood the concept of chemical shift. So what is chemical shift? So as we were saying that a molecule is made up of different nuclei. It is made up of and all these so there are different protons, right? Different hydrogen nuclei, and all these hydrogen nuclei are in different chemical environment, right? And because they are in different chemical environment, when you apply an external magnetic field, so each nuclei has its local magnetic field, produces a local magnetic field. Now, in presence of the external magnetic field, depending on this local magnetic field, the nuclei will shift in the there will be a shift in the you will you will observe a shift when you record the 1D NMR spectra, right? So one thing to important points we had discussed these concepts, so we will not again go into much detail. The important points we will discuss today. So the chemical shift value does not change with the spectrometer frequency, does not change with the spectrometer frequency. So that is the main purpose of we know that the chemical shift is reported in ppm value. So why does it not change with the spectrometer frequency? Because this is because we are what we are doing is we are taking the difference of the frequency at which we are observing or we are calculating the shift of the nuclei with respect to a reference frequency. Okay, with reference frequency, and then we are dividing it by the spectrometer frequency. So that is why what is happening in the ppm scale. In the ppm scale, there will be no change in the So if, for example, you are recording the spectra on a 500 megahertz spectrometer, or you are recording it in an 800 megahertz spectrometer, you will get the same chemical shift for a proton nuclei of, for example, you are recording the ethanol spectra. For example, you will get the same whether you record it on 700 or a 500 megahertz spectrometer. So that is what it is written here. So this is an important point. The precision and frequency. The frequency will, however, change with the change in the spectrometer frequency. So in the Hertz scale, the separation or resolution between the peaks increases on increasing the spectrometer frequency. Okay, so when you increase the spectrometer frequency, what will happen? When you increase the spectrometer frequency, in the Hertz scale, there will be more the resolution of the separation between the peaks will increase. But in the ppm scale, we will obtain the same ppm value of the whether you record it on different spectrometers. So that is what is written in the ppm scale. The sample frequency is subtracted from the reference frequency and divided by the spectrometer frequency. Hence, on increasing the spectrometer's frequency, the peak separation does not change. Okay. Now the next point is J coupling. So what is J coupling? J coupling, or we know that in a molecule, for example, one proton is bonded to the, or it is coupled, or we can say that one new proton is coupled to other proton through bonds, right? So for example, you consider a molecule ethanol, CH3 CH2 OH. Now the methyl proton is coupled to the methylene proton, right, through bonds. So that is what is J coupling. So J coupling is the yeah, it is through bond interaction, or it is also known as spin coupling is also called as spin coupling. So J coupling between two NMR active nuclei depends on the gyromagnetic ratio, the number of bonds separating them, conformation of the molecule, hybridization state of the bond, and substituents attached to the C13. So we had looked into all of these in detail. So if the proton is connected to an electronegative nuclei or electronegative atom, then there will be deshielding, and the nuclei will show a further chemical shift. Then depending on the hybridization state. So if it is an alkene or an alkyne, a double bond, triple bond, sp2, sp3, depending. So that also controls the electronegativity. Then the conformation of the molecule, right? So the conformation of the molecule, because it's basically the phi, the dihedral angle phi that controls the value of the J coupling. Okay. So and the gyromagnetic ratio uh, will also control the value of J coupling, and the area under the peak. So when we record a 1D NMR spectra, the area under the peak, what does that give us? It gives us the number of protons that 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 is resulting in the spectra, or that is the peak that we are obtaining, the intensity of the peak, that is proportional to the number of protons that is present in that nuclei. Okay. Now, the value of J coupling between two atoms does not depend on, so we just now discussed this, the spectrometer frequency, the type of nuclei involved, the structure of the molecule, number of bonds separating them. So it obviously depends on the number of bonds separating them, the farther the, or if the distance between two nuclei increases, or if the number of bonds between the two nuclei increases, then the J coupling value also decreases between the two nuclei. The structure of the molecule, right? It will also depend on the structure of the molecule, the type of nuclei involved. So C13H1 coupling will have a different value than H1 coupling, or um, then C double bond C will have a different coupling, right? So it depends on this now, on the nuclei, but it does not depend on the spectrometer frequency. Okay, it does not depend on the spectrometer frequency. Now, the highly downfield chemical shift of aldehyde proton is directly attributed to. So the answer for this question is the magnetic anisotropy of the molecule arising from the carbonyl function group. Now, in an aldehyde molecule, where has a general formula about RCHO, right? RCHO. So this proton which is directly bonded to the carbonyl group, that has a that will experience a that will experience a different chemical environment, or it will or the uh, uh, then the proton which is bonded to the other that is on the other side of the carbonyl group. Okay, so that is called magnetic anisotropy. So aldehyde protons come downfield at 9 to 10 ppm. Any proton that remains attached to a carbonyl group lies in a deshielded region compared to a hydrogen which remains attached to a methyl group. Okay, so if it is CH3CHO, okay, formaldehyde, acetaldehyde, C3CHO, then this CH3 is bonded to directly bonded to carbon, and then it is bonded to the carbonyl group. So that then compared to the proton, which is directly bonded to the carbonyl group. So depending on this, it will experience a different magnetic anisotropy. Now try to answer this question. Among the following molecules, which molecule will have the most downphase shifted methyl proton? So what are the factors that control the shift of the proton? The shift of the methyl protons, how what con so just now we looked into that. The what are the different factors that control the chemical shift? So it depends on the type of nuclei to which the this group is bonded. To which the group is bonded. So you see here the CH3, CH2, CH2OH. This proton is so methyl proton. So here in this question, you have been asked to find that which molecule will have the most downfield shifted methyl protons. Means it is here in this question they're asking about this CH3 proton. So in this CH3 proton, if you see this CH3 proton is very far away from this electronegative oxygen group, hydroxyl group. So so it is in a more shielded environment. So because it is in a shielded environment, it will be very near to the reference, or it will be near to the chemic to the ppm of the ppm value of the reference compound. Then as we decrease the number of methyl groups, the CH2 groups, you see this CH3 is coming closer to the electronegative group. So in this case, in this third option, this methanol, CH3OH, you see that CH3, this proton is in very close contact to the oxygen, electronegative oxygen atom. And so it will be in a very deshielded state. So in it is since it is in a very deshielded state, the downfield shift of the methyl protons in the methanol molecule will be much higher. It will be much higher than these options, right? Where there are more number of CH2 groups that are added between this methyl proton, with the methyl group and this OH group. Okay. Okay, so in methanol, the methyl proton is near to the highly electronegative oxygen atom, right? Resulting in a greater deshielding effect and a more downfield shifted chemical shift value. As more methyl groups are inserted between the methyl proton and the OH group, the ppm value shifts upfield. This is because the distance between the methyl group and the electronegative atom increases. So these are basic concepts. Now, okay, now try to answer this question. So which of the following C13 coupling is strongest? So for this question, if you have a rough idea of this of these values, then it will be difficult. It will be easy to answer. So remember this C13 single bond coupling has a J value of 35. This C13 double bonded, it has a J value of the coupling constant value is 70. And in a C13 triple bond, the J value is 170. Okay, J value is 170. So you see here, the value of J coupling is highest for this C13 triple bond. Okay. So C13 coupling is strongest for the triple bond C13 J coupling. We will move to the next question. In a molecule, a given proton A has a J coupling of 5 Hertz with two other protons and 10 Hertz coupling with another proton. How many J multiplet lines will be seen for proton A in the proton NMR spectra? So there is a proton A. So today I do not have this writing pad. So you have a proton. You have a proton A, right? It is J coupled to two protons. And the coupling constant between this is 5 Hertz. It is J coupled to two protons by 5 Hertz. So these two protons are equivalent, right? The two protons, which is to which it is coupled by 5 Hertz, is equivalent. So it will split. It will split the proton of A into a by following this n+1 rule. So it will be split into a triplet, right? Into a triplet. Okay. Now, once it splits into a triplet, then there is another proton. The other proton, which has a coupling of 10 hertz, that will again split these the three peaks into doublets, right? So the first peak will be split into two, then the second peak that will be again split into two, and the third will again be split into two. Okay, the third splitting that will be further be split into so total how many J multiplet lines we will have? We will have six. So the proton A will be split into a triplet by two protons, which has a J coupling of 5 hertz. Now each of these peaks in a triplet will be further split into a doublet by proton, which is J coupled by 10 hertz. Okay, further split into a doublet by proton. So you get three peaks, and then these three splits. Then these three peaks will further be splitted into two more peaks by this proton, which is J coupled by 10 hertz. Try to answer this question. A peak, I hope this is clear. So we have solved lots of questions based on these concepts. You can go through those lectures like once again. So a peak in a proton NMR spectra is located at 1.5 ppm from the reference on a 400 megahertz NMR spectrometer. If the reference is set to 0 ppm, what is the separation of the peak from the reference as calculated in hertz scale? So so a peak in a proton NMR spectra is located at 1.5 ppm from the reference. Okay, from the reference here, the reference compound is TMS. TMS. So the usually what we do, we take them, or in this question also, the reference, the chemical shift of the reference compound is taken to be zero. Now, if we take this as zero, then we have relative to zero, there is a peak shift of 1.5 ppm. Okay, and now, in hertz scale, what will this 1.5 ppm correspond to? So we had looked into, we had solved many of these questions in week two, I guess week two problem solving session. So what is done? You can basically consider that 1 ppm is equal to the spectrometer frequency. So you have to multiply 1.5 into 400 megahertz. So that value you get, that will be the the value in the Hertz scale. Okay. So what is basically chemical shift? Delta. Delta is nu A minus nu. This is not nu naught. I will change this one. This is actually the reference compound. Nu of the reference compound divided by nu naught. Nu naught is the spectrometer frequency into 10 to the power 6. Now here the delta is given. The delta is given. It is how much? It is 1.5 ppm. And you are asked to calculate the value of this nu A minus nu reference compound. Nu A minus nu reference compound. So what you have to do, you have to multiply the chemical shift. The value of the chemical shift is how much? 1.5 ppm, and the spectrometer frequency is how much? 400 megahertz. So you multiply 1.5 into 1 ppm is what? ppm means parts per million. So it is 1.5 into 10 to the power minus 6 into 400 into 10 to the power 6. So you multiply 1.5 into 400. That will give you the value in the hertz scale. Okay. So basically, you have to calculate this value, nu A minus nu reference compound. Separation of peak from the reference. So that is this one, nu A minus nu reference. Okay, we will look at the next question. What is the typical chemical shift range of aromatic protons in proteins and peptides? So the aromatic protons have a chemical shift in the range of 6 to 8 ppm, mainly in the 7 to 8 ppm. Okay, so remember this figure. This shows the chemical shift of different functional groups. Okay, so in the methyl protons, you have the chemical shift around 1 to 2 ppm. Then if there is a CHNH2, this NH2 amine group, then the chemical shift in this range. And then there are aromatic protons. So in the aromatic protons, you will get in this 7 to 8 ppm range. Okay, and RCOH, also remember this, that the carboxyl protons shows the highest chemical shift. Okay, now yeah, so now let's move into some of the more concepts that we had discussed. So NMR experiment is a series of RF pulses with delays in between them, and the pulse sequence is a blueprint of an NMR experiment. So whatever 2D NMR 2D NMR experiments we had learned, we had seen the different pulse sequences. So that pulse sequence is the blueprint of an NMR experiment. So the gap between two RF pulses is called the delay. It is called as delay, and the delay is usually in the millisecond range. right? Delay is in the millisecond range. In a 1D NMR experiment follows the sequence preparation or relaxation delay. So what happens in the preparation or relaxation delay? So you have the NMR probe, and in the NMR probe you have the sample. So once you put the NMR probe inside the NMR spectrometer, you allow a time delay. You allow a time delay so that before this the magnetic field, before you apply the magnetic field, you apply a certain time, so that in this time the populations get, or the system can come in equilibrium. So that is called the preparation or relaxation delay. And after this period, there is an excitation or RF pulse, right? So in the preparation or relaxation delay, you allow certain time, and then there you apply the magnetic field. And once you apply the magnetic field, the nuclei will distribute between the two states, alpha state and the beta state. And then the excitation RF pulse is applied. So these are RF pulses, short burst of RF pulses, and then there is acquisition period during which the FID is collected. So the relaxation is the order of few seconds. Remember these points. It is of the order of few seconds. The RF pulse is of the order of few microseconds, and the acquisition period is in the order of seconds. Okay, is on the order of seconds. The value of relaxation delay. The relaxation delay is the time period during which you allow the system to attain equilibrium. So once this you apply the magnetic field, you allow time so that the spins can get distributed between the two states. So that is the period. That period is called the relaxation or the preparation period. Now, what is the value that you keep for the relaxation delay? As a rule of thumb, we set the relaxation. The value of the relaxation delay is set to 1.25 into T1, and the acquisition time is the duration for which the FID is collected, and the acquisition time depends on the T2 relaxation of the sample. Okay, so there are two. One is the relaxation or the preparation delay. This relaxation or preparation delay depends on the T1 relaxation of the sample, and the acquisition period depends on the T2 relaxation of the sample. T2 relaxation of the sample, and the acquisition period is usually set to 3 into T2 value. Okay, so what happens is this beyond three times the T2 relaxation value, the you will not get any signal. The signal starts decreasing, and what you will record after beyond the 3 into T2 time, you will only collect noise. So if you use that formula, I naught cos omega t e to the power minus t by t2. So if you put the value of t equal to 3t2, then you will find that the intensity signal has become 5% of the original signal, or of the initial signal, 5%. So there is no point in collecting the data beyond 3 times t2 value. Okay. Okay. Now, the FIT is amplified and then proceeded for ADC. ADC is analog to digital converter. So once the FID you collect the FID, and then it is amplified, and it is converted to analog to digital converter. And what happens? This signal will contain both the signal from the sample and the noise, which may increase the dynamic range and ADC overflow. So the dynamic range should not exceed the range of ADC. So if the solvent concentration is very high, then what will happen? There will be an overflow of the dynamic range will become very high. And once the dynamic range becomes very high, you cannot record the ADC. The ADC will overflow this dynamic range. So you cannot collect that much high data. So that is called ADC overflow. And the carrier frequency we had looked into, we had seen these in detail: carrier frequency, frequency, signal aliasing, or signal folding. Okay, so carrier frequency is the frequency of the center of the spectrum. So for proton, the frequency range is kept from 1 to 10 ppm. So the center of this frequency will be what? It will be 5 ppm. So in case of a proton spectra, the 5 ppm is the carrier frequency. Okay, it is the carrier frequency. Unfolding or aliasing, why does it takes place? If the spectral width is spectral width is not selected correctly. So if the spectral width is kept very short, then what will happen? The signal that is outside the spectral region, that will fold into the region of the spectral width. Okay, so if we want to find if there is if the peak that we are getting, is it because of peak folding? Is it because of peak folding? Then first we will increase the spectral width, and then we will again, if so on increasing the spectral width, if we see that the peak that we were getting, right? That is not there. Then we can say that this peak is coming because of peak folding, and improper shimming results in increased line width of the peak. So what is shimming? Shimming is the also known as locking. So the magnetic field after this probe is after the probe is put inside this NMR spectrometer, we allow shimming so that we lock the magnetic field fluctuate. Okay. Okay, we will try to complete this. The T2 relaxation time of a molecule is 100 millisecond. Based on this, which would be the most likely, which would most likely be the acquisition time to be used. So remember the acquisition time. Okay, acquisition time is not the period time period for data collection is not proceeded beyond 3 times the T2 relaxation of the nuclei. Okay, because beyond that point there will be the signal intensity will decrease. So you can, that is the FID. If you see, FID is equal to I naught cos omega t e to the power minus t by t2. You can put the value t equal to 3t2, and you will see that the beyond 3t2, the intensity value has dropped by 5%. So that is why if you do this, so in this question, 3 times t2, so 3 into 100, that is 300 millisecond. So till 300 millisecond, the data can be recorded. Now in the T1 relaxation of a proton is 2.4 second. T1 relaxation, what we just learned, the acquisition delay is or the relaxation delay. It depends on the T1 relaxation value of the sample. So it is 2.4 into, it is usually kept 1.25 times the T1 relaxation value. So it is 1.25 into 2.4 will give you 3 seconds. Now moving to the next question, which of the following parameters affects the dynamic range in an NMR spectrometer? In an NMR spectrum, uh, dynamic range. So the dynamic range, it will depend on the concentration of the solute and the solvent. So if the solvent concentration is very high, then the dynamic range, then the dynamic range will be very high, and it will go beyond the range of ADC, or the when you convert this into after amplification, you take the ADC, then as the dynamic range has become very high, that cannot be captured. That cannot be captured by the the analog to digital converter, and so uh, you will see I have ADC overflow. Now here in this question, so this question, this questions we had seen such type of question. So it has two proton peaks, one with one showing triplet, another quartet. So the answer for this is ethanol. Why is it ethanol? Because if you see CH3 CH2OH, so the most downfield shifted will be this OH proton, and then you will get this methylene proton, and then you will get the methyl proton. Now this CH3 is coupled to this CH2, so this two protons will cause splitting of this CH3 into a triplet. N plus one rule, you apply the N plus one rule, and you will get the answer. And this methylene will be split a quartet, into a quartet by this methyl group. Okay, and but if you apply these N plus one rule, you will see that now triplet and quartet you will not get. For CH3, CH2, CH3, you will get only how many peaks? You will get only 2 peaks, right? One for this methylene group, and one for the methyl proton. One for the methyl proton, and these are equivalent. So if you draw the symmetry, line of symmetry will pass through this CH2, and these CH3 protons are equivalent to this CH3 proton. So in a low resolution spectrometer, you will observe only 2 peaks, and there will be no peak splitting. Okay. Similarly, you can apply these N plus one rule, and you can see what will you get. Now, the question, which of the following does not increase the signal to noise ratio of an NMR experiment? So sample concentration, we for NMR experiment, the main requirement, or the main one of, if you it is a disadvantage also, because you need the protein sample in very high concentration, in a few millimolars, in like 100 millimolar, no, in 100 micromolar range, or in 1 millimolar range. In millimolar range, the sample concentration is required, because the NMR is an insensitive technique. So sample concentration, if you increase, they will get better signal to noise ratio. If you increase the magnetic field, then also the signal to noise ratio increases. It varies as B naught to the power 3 by 2. And the type of probe used, that also controls the signal to noise ratio. So the answer for this question is all of the above. Okay. Now, STD-NMR, in STD-NMR was discussed in the last week. So this is saturation transfer difference NMR. So this technique can be used for studying the protein ligand interactions. So mainly this is used in biopharma. It is very useful technique in considering the requirement of a biopharma industry. So you have multiple ligands and you want to screen that which ligand is binding to the protein. Then in that case, you can perform this STD-NMR experiment. The binding but the binding study. So the binding interaction, it can be detected by this technique is in the range of millimolar to micromolar. Okay, the size of the ligand to protein should be 15-fold low. So if the ligand is for example 15 Dalton or 10 Dalton, then the 150 into 10, 150, okay, will be the size of the protein. And the protein concentration required is in few micromolar, while the ligand is required in a higher concentration. So what is done in an STD-NMR experiment? You selectively saturate the protons that are present in the protein, and then you first record a reference spectrum, and then you saturate the protons of the protein molecule, and then you take the difference of the two, and the difference will give you the if the difference will give you the this spectra will give you this. This is what is recorded in STD NMR. So if you see that there is a change in peak intensity, so you see this is del A, this is delta B, this is of the proton peak of the protein. This is the proton peak of the protein. You are selectively saturating the proton peak of the protein, and then you are recording the spectra. So you see that on saturating this, you are seeing that the signal for the ligand, okay, the signal for the ligand has decreased. So this indicates that there is an interaction between the ligand and the protein. Okay. Now try to answer this question. Which of the following dihedral angles in a peptide can be obtained from proton NMR spectrum? So just now we were discussing about J coupling. So the J coupling value also depends on the conformation of the protein. So conformation of the protein, why does it depend? Because this J value depends on the phi dihedral angle. So how is this related to the J coupling is related to the phi dihedral angle by this formula. This is known as Karplus equation. So the Karplus equation is A cos square phi plus B cos phi plus C. So this J coupling and this once you know the J coupling, you can get the dihedral angles also. Okay. So what is the dihedral angle between two neighboring residues? That can be calculated. Torsion angles. And what is the correlation between the chemical shift and the secondary spec structure of protein or peptide can be obtained by using. So these are different softwares. Talos, CCP-NMR, Chiara, Sparky. So the correlation for between chemical shift and secondary structure of protein, if you have to determine, then the chemical software that is used is Talos. Okay. So what is Talos? Talos is torsion angle likelihood obtained from shift. It is an algorithm that can be used for calculating the phi and psi dihedral angles. Okay, so phi and psi. So after the peak assignment, so when you are solving the structure of a protein, though after you have you will get different peaks, right? You will get different peaks if you record the HSQC spectra and you assign the peaks for which is the amino acid that is corresponding to each peak, and then once you have assigned the peak, once you have assigned the amino acids, then from this the phi and psi angles can be predicted. Okay, so for each amino acid, the 5 chemical shift values, the each alpha, C beta, CO, and NH values are required, which are then matched with the database to obtain the dihedral angles. So you will obtain the chemical shift values of these H alpha, C beta, CO, and you have a database. And based on the chemical shift values that you obtain, that will from the database you can predict that this chemical shift can correspond to which phi angle or which psi angle. So that is done by this Talos software. Then there are Sparky for three. This is for assignment of peaks, and these are other softwares that are used in NMR spectroscopy. Then in a general, so just now we learned this, that in general, an appropriate range for dissociation constant between the target protein and ligand in an STD NMR will be. So in an STD NMR, the binding interaction or uh, the binding between the protein and the ligand That is in the range of micromolar to millimolar. So it is, the answer is 1 millimolar to zero point 0.1 micromolar. Okay. So what is done here? The protein is taken in micromolar in a few, you can take a few micromolar of the protein while the ligand is taken in millimolar concentration. So the tertiary structure of proteins can be determined mainly by using cozy peak intensities, interresidual distance restraints, proton chemical shift, and toxi peak intensities. So cozy peak intensities will only give you the nuclei to which it is directly coupled, right? That will only that is the only information it will give you. Toxi will give you the information to all other protons that it is correlated. But in case of a peptide, it will if you record a toxi experiment, then it will only give you the particular or intra residual information. Intra-residual information means it will give you the correlation between the C alpha, H beta, H gamma. So if there is is an amino acid, consider arginine. So so you will get a particular spectra for arginine. You will get a particular spectra for alanine, glycine. So based on this, you can only get the intra-residual information, but you will not get inter-residual information. So if you want to get the inter-residual information, so which amino acid is close to which amino acid, right? That information can be only be obtained if you record a nosy spectra. So the nosy will give you the distance between two residues. Between two residues, what is the distance between the two residues? That will only be obtained if you record a nosy spectra, because in the nosy spectra, from the peak intensities, you can calculate the from the peak intensities, you can calculate the distance R, right? Rij. I is inversely proportional to the sixth power of the distance between the two nuclei. We learned that in the last class. So you can also, not only you can um, you will know what are the amino acid peaks, but also what is the distance between two amino acid peaks, that also you will obtain. So from that, you can understand the tertiary structure of protein, which in a tertiary structure of protein, one amino acid is close to other amino acid. There is folding of the protein, proper folding of the protein. So only if you know the distance between two amino acid residues, you can determine the tertiary structure of protein. Now this question, the STD amplification factor versus concentration, it gives insight about what. So the STD amplification factor, what is it? It is I naught minus I saturated by I naught into ligand excess. So this is the formula. And this I naught is what? I naught is a non-saturated signal. I sat is the saturated signal. Okay. And so if you calculate this STD amplification factor from here, what you can get? You can get different information. First information you can get is what is the active ligand concentration. So how much ligand or what how much protein you will require, how much protein is required for the experiment. That also you can get once you get the active ligand concentration. And it also helps us to determine the KD value, the dissociation constant value also you can get from the STD experiment, right? So what is the binding Oh, how strongly or how weakly the ligand is binding to the protein. Those information can be obtained from an STD, and also it also helps to identify that what are the particular residues on a ligand, which particular protons, or if there are the ligand will have protons, so which particular protons in a ligand is specifically interacting with the with that of the protein molecule. So those information also you can get from an STD experiment. So that this was the